Okay, this is the second time I forget to hit the recording button. So for those of you who are watching later, sorry about that. But the good thing is that I've only been recapping what we've covered in the last class, so I haven't covered anything new. Thank you, Mohammed. All right, so general inflation rate. So I can treat the CPIs like prices, right? And then I can divide and raise to the power 1 over n minus 1, and I get my general inflation rate F bar, which is kind of nice. I can also get specific inflation rates, these F sub j's, for a specific segment of the economy, right? And we said that we have multiple examples, and we see here in this table, you can get the inflation rate for anything in particular, like for example, movie tickets, baseball tickets, cars, right? Whatever. Or you can have something general that is based on this market basket, which is the CPI. Right, and we covered this example. We just did it now. Okay, and so here's where we stopped. We started talking about actual dollars and constant dollars, right? And I finished with an example, which I'll just remind you of in words, right? I told you I can give you the following two cash flows. The first option is I tell you I'm going to give you $100 in actual dollars every year for a number of years, let's say for the next 10 years, right? And so what that means is that every single year I'm going to show up, knock on your door, and I'm gonna greet you with a $100 bill. And I'm gonna give you that money. But we know, of course, that the $100 bill that I give you at that point in time is, well, I mean, if we're talking about like 2-3 years from now, is gonna be worth less and is gonna be able to purchase less and less compared to right now, right? However, I mean, that's what I'm gonna give you, right? So that's actual dollars. And that's actually what we've been using in chapter 2. And if you remember, we had this in the assumptions that we're going to be dealing with actual dollars. What about constant dollars? So the other option is I tell you I'm going to give you an annual payment of 100 constant dollars for 10 years, let's say, right? For the same number of years, for example. And so here what I'm really saying is that I'm going to give you an amount every single year that has the purchasing power of $100 today, right? So I show up in today and I give you, for example, $100. I mean, if I'm starting from today, let's assume for the sake of example that I start from today. So I show up, I give you $100, right? You can buy, let's say, something. I don't know what that something is. What can $100 get you? A lot of things, but I'm trying to think of like one item that is priced. It can buy you an Amazon Prime subscription, which I think costs $100 up until recently, right? I show up 1 year from today. Now, because I'm giving you 100 constant dollars, I have to consider inflation, and I have to see how much I should really give you, like how much actual money. See here, actual money I should really give you for you to have the same purchasing power that you've had 1 year in the past, right? And so if the inflation rate was 5%, that means I'm going to have to give you 105 actual dollars, which is the equivalent of 100 constant dollars. Because with that 105 actual dollars, you can buy the same amount or the same things that you could buy with $100 1 year before, right? And so you see here the difference. The constant dollars in particular, they include a measure of worth, of how much money is worth. Whereas with actual dollars, it's just an amount that I'm giving to you. And that amount carries some inflation, right? Because it's worth a little bit less than before, right? And so constant dollars, we're going to refer to them, or we're going to, so in a cash flow, so let me switch to a pen. You remember this A sub n is the payment at time period n. So in a cash flow diagram, right? So if this is year 1, so I have my payment A1 here, A2, right? And so on. I can give you a cash flow that has constant dollars. And in that case, we're going to use this A sub n prime to denote these payments, right? So if this is period 1, then this is A sub 1 prime. And then similarly here, we have A sub 2 prime, right? And as I mentioned, like in my example, you can have a cash flow that has either of these, right? I gave you the example first where I give you $100 in actual dollars. And I gave you the example second where the cash flow consists of me giving you $100 in constant dollars, right? Notice also one thing, well, two other things. So of course, there are these alternative names here that you sometimes might see. So constant is called real dollars sometimes, and actual dollars are sometimes called current dollars, right? Which is sometimes a little bit confusing to remember, but if you can, try to remember these or to memorize them. However, more commonly, I'll be using actual and constant, but maybe some questions are going to have these other terms in them. All right. And the other thing I want you to note before we move on is the following. Notice in my example with the constant dollars, I kept referring back to today. I said 2 years from now, I'm going to give you 100 constant dollars, which means I'm going to give you the equivalent of $100 today. I'm going to see what that amount is 2 years from now, and I'm going to give that amount in actual dollars to you. So notice here this reference to today. That means there is a base period, which I'm using to measure the worth of the money that I'm giving to you, right? And it's usually today. It's usually the first time period or the earlier time period that you're given in a question, but not always. Sometimes, I mean, I want maybe to frame it in such a way that I'm going to give you 100 constant dollars with the base period being 5 years from now. That can happen, but usually it is today, right? And we'll see some examples on like this base period business, right? So hopefully this distinction now makes sense. And so now that we know what these are, now let's see how we go from one to the other. So if you're given a cash flow in actual dollars, can you convert it into a cash flow in constant dollars and vice versa, right? And you may have noticed also from my example that we can do this, right? If I give you $100 in constant dollars 2 years from now, I can convert it and see how much I need to give you in actual dollars. So that already tells you like what the conversion process is like. Okay, so here's how we do it. So suppose I tell you the following. I'm going to give you in year 3 or 3 years from now, let's say, $1,000 in constant dollars. All right. And what I need to find is how much do I actually need to give you at that same time period. So I need to find the actual dollar amount that is equivalent to $1,000 today. Notice the base period in purchasing power. Question. Who was that? Muhammad, yes.
Yes, doctor. Are you recording the class?
I should be now, yes.
Okay.
Okay. Yeah, it seems to be recording. I hope it is. All right. So notice here that there's this base period, and this is time 0. So this $1,000 is measured in terms of like the purchasing power of today. But I'm going to give it to you 3 years from now, so I need to adjust the actual dollar amounts that I need to give you. And what you're actually given as well, I mean, of course, you can determine here that the number of years is 3, right? So the difference between the base period and the time that I'm giving you the money is 3. So we need to use that to adjust our calculations. So that's my n. So my n is going to be 3, right? Actually, I think it's measured from here, right? So here I'm giving you something in 3 years, right? And so my base period is at time period 0, and so my n is going to be 3. You're also given the average inflation rate, which is this F bar, which we've seen before, and we know how we compute it, right? We can compute it using the CPI, or we can compute it using, it's mostly, I think, using the CPI, right? That formula that we've seen before, it's CPI n divided by CPI 0 to the power of 1 over n. So this is in case you're not given this value. You can be just given an inflation rate, right? -1. So this is the average inflation rate for this market basket of goods. So I'm given my inflation rate, I'm given the number of time periods. How can I compute the actual dollars? Well, I mean, if you go back to my example, when I mentioned, for example, that the inflation rate was 10%, let's say, and 1 year from now, I'm going to be giving you $100 in constant dollars, and I need to find the actual amount. I just need to inflate this amount. So if it's a year from now, I'm going to give you 110 actual dollars, and that will have the same purchasing power as $100 today, right? And so that's exactly how we do it. So see here, I take my constant dollars. Remember, constant dollars have these primes. So I'm going to take that constant dollar amount, and I'm going to inflate it using the general inflation rates. And I'm going to inflate it a number of years, n, right? And so that's how we do it. And if you look at the what the formula looks like after we plug in the numbers, you will see that we take $1,000 in constant dollars. I need to move, because my base period is here, so I need to move 3 time periods. So I'm going to use the general inflation rate to inflate this 3 times. And that will give me the actual dollars that I need to give you in year 3, which you see here now. And that will have the same purchasing power as $1,000 today. All right, so this is the formula, and it looks very much like, I mean, if you see here, it looks very much like our F given P business that we've had before. It's pretty much the same thing. The only difference is instead of I'm using the inflation rate, the general inflation rate, this F bar. Okay, and we'll see some examples on this. So this is how we go from constant to actual dollars. And here's an example in a table. I mean, not in a cash flow diagram, but it's the same thing. Suppose I give you the following cash flow, and I tell you this cash flow is in constant dollars. So first, you take out this amount in constant dollars, and then you, you pay this amount, I guess, at the beginning, and then you withdraw all of these amounts here in constant dollars, right? And I'm asking you, what is the cash flow in actual dollars? Well, first of all, you need to be given the inflation rate, which, I mean, is here conveniently. So this is F bar. So you're given that F bar is 5%, which is nice. And now we just need to apply the formula. The formula says the following. I take my AN prime, right? And I inflate it for a number of times n. So A sub n, right? So this is A sub n, where this is actual, this part here. Actual, right? And this part here is constant. So if I want to find A sub 1, for example, I take the actual constant dollar amount, A sub 1 prime, and I inflate it, right? And so I inflate it. I mean, my n here is 1 because it's A sub 1, and I find the value to be 105,000. And you could do the same thing for these other ones, right? And so notice here that the base period is conveniently computed using period 0, which is what we typically are going to use. If you're given 2 time periods, always assume the earlier one is the base period, unless the question asks you to use a different base period. Of course, you can use other ones, but it's better to just stick with using the first time period as the base time period. Okay, so this is just a straightforward application of the formula, and we use the correct n at each point, and then we convert this cash flow that was given in constant dollars to a cash flow in actual dollars. Okay, notice here, just to like drive home the point, maybe we're not moving anything back in time, right? So this is still, so let me erase this stuff so I can illustrate. So this is kind of important because, I mean, this formula looks like we're moving things either forward or backwards. Like in this case, it looks like we're moving things forward, but that's not really what we're doing. We're just taking a payment at time 1, which is here in constant dollars, and we're converting it into its equivalent payment at the same time in actual dollars. Okay, so this is critical because, I mean, I can tell you to draw the cash flow here. It will have 5 time periods, and each of them will have payments, right? First one is negative, actually, at time 0. Right, 1, 2, 3, 4, 5, yep. And I can tell you to draw, and so you can indicate these amounts here. So you can put minus 250K, right, and then 100K, and so on. But you can also represent the cash flow diagram in actual dollars, and it will look somewhat similar, but the amounts are going to be different. Right, so here I have to say minus 250K at time 0, but then here I put 105K, not 100K. So this is constant, and this is actual, right? So make sure like you follow this point because it's kind of important. I don't want you to mix things up. We're not moving anything in time yet. We're actually going to move stuff later in time. I can still find the present value of this cash flow here, of this actual dollar cash flow, and I can find the present value of this constant dollar cash flow. But that's going to come later. For now, we're just taking a payment and converting it from constant to actual. All right, so let's see some examples. So if I ask you the following question, and I tell you, what would $30,000 earned in the year 1995 be equal? And when I say equal here, I mean really equal in purchasing power. The book just says equal for some reason, but I was hoping the book was more specific, like what it means by equal. And equal in this case means like equal in terms of purchasing power. So equal exactly in terms of the amount of stuff that you can buy. And so it's asking, what would this amount back in 1995 be equal to in 2011? And let's suppose you're given the CPIs for these 2 years. So the CPI or the index for 1995 is this much, and for 2011 is this much, right? And so from the question, I know it's asking me like, what is this amount in 1995 equal to in 2011? So that means I need to find sort of the actual amount in 2011, that gives me the same purchasing power as this $30,000 in 1995. And to do that, what do I need? Yes, Khalid?
You need to calculate the average inflation rate because you are giving the two CPIs. Then we will calculate the future value given the present value.
Exactly. So just to be maybe nitpicky on this point, avoid maybe saying future value and present value when we're dealing with conversions from constant to actual dollars, because I mean, you're absolutely right. The formula looks exactly the same. But maybe it's better to avoid it because maybe then you mix things up. You start thinking that we're moving things in time when we're kind of not really doing that. Okay, but you're absolutely right. So we need first to find, we're not given an inflation rate, which is always critical to convert from constant dollars to actual dollars. And so what we need to do is we need to compute it. And the way we do it, we've already said, if we're given the CPIs, I can treat them like prices. And so this is my F really for the CPIs, and this is my P, if you will. And then I'm gonna use F bar in this case. And I have N, which I need to figure out. And actually N in this case, if you just do 2011 minus 1995, it's gonna be 16. So the CPI is increased from this amount to this amount. From this amount here to this amount over 16 years. And I need to find the average inflation rate. So I'm given the two CPIs. I computed N, which is 16. I just plug in and I solve for F prime, and I find that it is 2.42%. Okay. Now, as Khalid said, I need to do the conversion, which is kind of like F given P, but I will just say it's a conversion from actual dollars, from constant dollars into actual dollars. So I take my 30,000, which is in constant dollars, and I need to inflate it 16 times, right? Because my period is 16 years, and that will give me the amount that is equivalent to $30,000, but this is in year 2011. So this is how much money I need to give you in 2011 to be equivalent and to have the same purchasing power as $30,000 in year 1995, right? And notice here that by default, we kind of assume that 1995 is the base period. So this 30,000 in 1995, that's sort of our base period that we're using for the sake of comparison. So if you're given, like in this case, you're given 2 years, take the first one to be the base period and do your computations based on that, generally speaking, unless the question hints or tells you to do something else. Okay. Oh, why 16? Because 2011 minus 1995 is 16. So that's the time period. Why not 17? Well, just do the math, right? Just subtract. It's 16 years. Okay. Well, in this case, so remember, if we're at 0 and I tell you I want something at 5, it's always going to be 5 minus 0, right? So 1, 2, 3, 4, right? So how many years in total here? I have 5 years. So don't do the b minus a plus 1 thing unless you're chopping off this 0. If you're not including the 0, then yes. Even in this case, right? So in this case, no, in this case, it's because the interval that you're looking for is the following, is 0 to 5. So you want this interval. And so in that case, it's going to be, no, wait. Okay, let me restart. So let me go back from the beginning. So if you're at time period 0, and I ask you for something after 5 years, then how many years do we have? It's just 5 minus 0 in this case, right? And so similarly here, if I'm at 1995, so this is like my time 0, and then I want to find how many years, right? So I need to count how many jumps I make. Do it this long way. So the b minus a plus 1 thing, I think I used that in a very specific example where I was actually chopping off something. Like I'd have to remember what that example is. So I think I told you that. Maybe you asked me about it, I think, as a question in like an office hour or something. And I told you to use b minus a plus 1. But that was for that example. But in general, what you really need to find is the number of jumps, right? The number of compounding periods that you have between two time periods. And of course, in this case, you're not actually going to count 1995. So that's what I was trying to get at, and then I got confused, right? So you're actually removing 1995, right? And you're starting your count from 1996, really, because that's the first year that you complete. And in that case, you can do the B minus A plus 1. So you can do 2011 minus 1996 plus 1, and that will give you, what is it, 16, right? So hopefully this made sense. I'm sorry, I confused myself and then confused you all. But basically what I'm saying is that 1995 is not included here, right? Because you need to count the number of years. It's just like your birthday, right? You don't start counting, like if you're born on 1990, you don't count 1990, 1991, right? You start counting from 1 year after that. So 1991, 1992, and so on, right? So, I mean, this is just a counting thing. So make sure you understand this. Make sure you count how many jumps there are and see if it is actually 16 or 17. And of course, it will be 16. And then try to convince yourself why it is 16. Because again, we're not counting 1995. So you can just subtract directly, right? 2011 minus 1995, and that will give you 16. Okay? All right, so now that we've covered that part, let's see how we can do the reverse, how we can go from actual dollars to constant dollars. And of course, there's not much to say here because, I mean, you can already see it from the formula, right? It's basically the reverse of what we've done before. So, I mean, if you had the formula before, you can just derive this formula here, right? By just moving things around. And you see here, the only difference is that, of course, these guys are now switched because we want constant dollars from actual dollars. And the exponent is now negative. So this is kind of like P given F, right? But I will keep saying, I mean, this is converting from actual dollars to constant dollars, just to be consistent and to be clear, okay? And so see here, the example, we're given sort of the reverse problem, right? Exactly the reverse. And if we apply the formula, in this case, we're going to get back our original $1,000, right? So there's nothing new here. It's just going in the opposite direction. And here's another example, sort of using a table where we see this in action. So I'm giving you the average inflation rate, which is F bar, at 5%. And I'm giving you a cash flow in actual dollars. So this time I'm saying I'm going to give you this actual amount of money every single year for the next 4 years, right? Or 5 payments, right? Starting from today. And I want to find the cash flow, the equivalent cash flow in constant dollars. So again, what I need to do is I need to take each payment at each time period and convert it to its equivalent amount in constant dollars at that same time period. And here you see, I just apply the formula, like straightforward. Again, I'm kind of assuming that my base period is here. And so that's why these are all relative to the base period, right? And so I apply the formula, my exponent is negative. And by the way, this process, so this formula here, sometimes I'm going to refer to it as discounting, or maybe sometimes deflating. So I'm going to take this amount here, and I'm going to discount it or deflate it in order to convert it to this amount here, right? So this is just the process of going from actual to constant dollars is sometimes called discounting, or discounting, or deflating or deflation, right? Okay, so now I found my cash flow in constant dollars, right? And so let's see what this really means, right? What this means is that at year 0, the amount that I'm going to give you, which is $20,000 in actual dollars, has the purchasing power of $20,000 in constant dollars. That's kind of what we expect, right? Because we're comparing things at the same time, at time 0, which is right now, and the base period is right now. So actually, like $100 today has the purchasing power of $100 today. I mean, that's kind of obvious. So these amounts are going to be the same. The difference, of course, is 1 year from now, because if I give you $100 1 year from now, it's going to have less purchasing power, which is what we expect and what we see here. And so the purchasing power goes down because I'm giving you the same amount, but there is inflation, right? And so this makes sense. And we can actually compute. So let me erase this. The loss in purchasing power as a percentage, right? So in year 0, we're not losing anything, right? I mean, as we said before. However, in year 1, I've lost how much? Where's my pen? I've lost 4.76% from the 20,000 constant dollar purchasing power that I've had a year before that. And of course here I keep losing. So here, I mean, this loss is always relative to the base period. So here I've lost 9.3%. And then of course, for example, this last time period, I've lost 17.73% of purchasing power in year 4. So for the same actual dollar amount, I keep losing purchasing power, and this is how much I lose. Okay, let's see some more examples. Suppose you're given this following table, which has the winners of the US Open, I think, yes, US Open Golf Championship tournament. Okay, so 2002, this was the winner, Tiger Woods, and he got this much in actual dollars, right? So this is actual money that was handed to Tiger Woods at that, like in that year, and so on, right? So you have all these guys who won the tournament, and these were the amounts that they were given as prizes. All right, and it's asking you the following. It's asking you to convert these prizes into equivalent prize money, but in 2006 dollars. So the first thing that you notice here is that we're not actually using 2002 as the base period. So here the question explicitly asks me to use 2006 as the base period, right? And so I need to use this time period here as the base period. So I need to be careful. I need to adjust my formulas a little bit when I do that, because the base period is now in the future, right? And also, not only that, of course, by the way, before we move on, because I'm not going to have the table in the next slide, you're given the consumer price indexes for those years, right? So you see here, you have all the values, and that's going to be useful to us. You're also asked to do the following: to determine the growth rate of the prize money in actual dollars over 4 years. So if I go back here, erase my pen. So here, the price keeps going, as you can see, in actual dollars. And it's asking you, what is the average growth rate? Another name for that is basically the inflation rates, right? In actual dollars. We're also asked to find the equivalent prize money in year 2006 dollars, which, I mean, was the question that we were asked before. So this is going to be, I mean, these are like parts, right? So this is part A, part B, part C, part D. We're going to see each part on a separate slide. And then after I find the equivalent prize money in 2006 dollars, I need to find the growth rate of that prize money. So now it's in constant dollars, not in actual dollars, right? So I need to find two growth rates. How much is the prize growing in actual dollars, and how much is it growing in constant dollars on average over 4 years? And after that, finally, it's saying if the current trend, which means the current increase or growth in actual dollars, if that keeps going, what would be the expected prize money for the winner in the next year, right? 2007. Remember, here we stop at 2006. So in 2007, if these here keep growing at the same rate, at roughly the same average rate, what is going to be the value here? Okay, so that's at the very end. So now let's see how we do this part by part, like one part at a time. So the first part is I need to find the growth rate, which is also known as the average inflation rate. So I mean, because here, like, I mean, you should just know this. I think that growth rate is the same as the average inflation rate, especially if we're dealing like with actual dollars, right? And so I need to find the average inflation rate of the prize money in actual dollars. And we've already seen how we can do that before, right? This is going to be my F, the last value, and the first value is going to be my P, right? And I'm going to apply the formula. And if you remember, just to refresh your memory, the formula looks something like this: 1 over n minus 1. And of course, again, n here is 2006 minus 2002. So you get 4. And you can plug in this formula and you will find the correct value of F, which is the average growth rate of the prize money in actual dollars, right? So this is what is written here. I mean, here they're substituting, but of course, once you manipulate the expression, you will be calculating this basically, right? And the result is that on average, the actual dollar prize money grows by 5.2%. Okay, so hopefully that's straightforward, because it's kind of exactly the same as what we've been doing before. Now comes the new part. So part B, let's go back here. We need to find the equivalent prize money in the year 2006 dollars, right? So our base period is 2006, right? So the way we do it now is, well, first of all, we have two, we have something missing here, right? And so what's missing, I mean, conveniently, they've put a column for it in the table. What's missing is the inflation rate. And actually, so here's a point that I want to make, is that if you're given consumer price indexes or indices, right, for every year, then that's a hint that you should compute the annual inflation rates and not the general ones, right? So don't just use this inflation rate that we've had here in this example. Because you're given these yearly values, you can actually be more specific and more accurate. Because remember, like, this is average. This kind of takes out the noise that you see. But this here, I can use it to calculate a yearly inflation rate from one year to the next, right? And so that's the first step I need to do. So I need an inflation rate, but however, the point here is because you're given these values, you can compute each year's inflation rate and then use each year's inflation rate instead of using the average one. So that's the first thing, right? And then I need to convert these actual dollar amounts into constant dollar amounts with 2006 as the base period, right? And if I do that, if you look back at the formula, the way we've computed it, I need to adjust my n in this case, right? Because now the base period is in the future. So it's kind of like I'm doing f given p, right? It's still going to be an amount that is at year 2002, but the way it's measured is with respect to a year that's in the future, which is 2006, okay? So that's like one slight difference from the computations that we've done before. So let's see what this looks like. Let's go through the solution. So here, of course, if I'm computing something in 2006, right, I can just take this amount here and put it here. Nothing is going to change because, I mean, constant dollars in 2006 are equivalent to actual dollars in 2006, right? So there's no difference here whatsoever. The difference comes, of course, the year afterwards, or the year before it in this case, because we're going backwards in time, right? So this amount here, I need to do some work. And the way I do it is, notice here, I first compute an annual inflation rate. So here, notice that these two values are here. So I'm using my f is going to be here, and my p is going to be this one. I raise to the power 1 over n. And in fact, n is, in this case, is going to be 1 because it's just 1 year minus 1. I compute the annual inflation rate for that year, for this final year, from 2005 to 2006. And I find it is 3%, right, 0.03. Now, I can use that to convert my actual dollar amount in 2005 to a constant dollar amount measured in terms of 2006 dollars, right? And so the way I do it, because I'm kind of going to the future, my exponent here is positive, right? In this case, it's +1, right? So that's the difference here because the base period is in the future, okay? So be careful with that. And of course, it's just 1 year, so I apply my formula, and this is the amount that I should put here. So I should put that here. Okay, so that's this value, right? So that's 2005. Now let's do 2004. Of course, I can start doing it sort of the same way. I can find, let me erase my pen so I can see. I can find the annual inflation rate for that year, which means that this is going to be my f, this is going to be my p, right? And that's what you see here. Again, I mean, n is going to be 1 because here I'm just finding the average over 1 year, if you will. And I find that this is the inflation rate, which I should put here, right? I'll put it maybe, I mean, I don't know. It depends. Like, do you want to put it here? Do you want to put it here? Up to you. As long as you're clear about what this is, right? I think maybe it's better to put it here because then you're clear that this amount is inflated. No, actually, the way the book does it, if I remember from the slides, they would put it one time period afterwards, right? So put it here. Okay, it doesn't matter. In any case, I found the value that I want, okay? Now I need to convert this value into this value here, constant dollars measured in the year 2006 dollars. The way I do it is, of course, I need to be careful. Now I have annual inflation rates, so I can't just use the formula that says raise something to the power n, because remember, that assumes that whatever rate, whatever I or whatever f I put in here is constant. So that's not the case here, so I need to go back to the original way, which is doing it like this, 1 plus f1 times 1 plus f2, etc. Okay? And so that's why here you see we're taking this value that we just found, which is the inflation rate. So this is going from this year to this year. And then I put in the other inflation rate, which is going from this year finally to 2006. Okay, and the amount that I find is the amount that I should put. So this is for Goosen, so I should put that amount here. Okay, so hopefully this is clear. Like, we did things in steps. We first needed to find the inflation rate. However, as I said, we find the annual inflation rate in this case because we're actually given yearly data. So we can use that data to find the annual inflation rate. And then finally, what I need to do is I need to convert into constant dollars. However, the difference here in this example is that the base period is in the future. So my exponent needs to be positive because it's kind of like finding f given p, not the other way around. Okay. Now let's look at, okay, before we do that, Mazen?
Yes, look, in the average inflation rate, we use the
Yes.
actual dollars to calculate it.
Yes. Yeah, well, actually, so what we found here, I mean, this is where it gets a little bit confusing, I guess, because it is called the growth rate. We're just computing sort of the growth of this, right? But we also call it the average inflation rate. So there are two ways you can find the average inflation rate. I'm not sure if they actually give the same value, because you remember average inflation rate, I can find it from here, from using the CPIs. I can just do, I can do this. I can do 200.43, which is this value here, divided by 179.8, right? And then I raise this to the power 4, 1 over 4, sorry, minus 1. So this will give me the average general inflation rate. I'm not sure if it's actually the same value as this, maybe not, because this is general. I think the difference is this is general. So this includes all of the things that go into the market basket. Remember, CPI includes a lot of things that people commonly buy. So this is the general inflation rate for the whole economy. Whereas in this case, the growth rate that we found, or the average inflation rate, is actually specific to the golf prize money, right? So that's maybe where the difference is in this case. I'm not sure if that answers your question. If not, let me know.
Yeah, it answered it because I was confused as why we shouldn't use the consumer price index in this case.
Okay, yeah. So just to repeat, just to make sure the thought is clear and the answer is clear to everyone. So in this case, the way the question is asking us, like it's asking for the growth rate of the prize money in actual dollars. This is the same as the average inflation rate for that prize money, just for the prize money. Remember, we can compute inflation rates, average specific inflation rates for anything, right? And so that's what we found here. So this F is specific. This is for golf prizes, right? Okay. The CPI, I can use it to compute an F, right? And that F is actually the average general inflation rate for the whole economy. And so that is F bar. Okay, so these two are two different values. It just depends on like what the question is asking us, and of course what we're given. Because you can use this F bar to compute these this value here. But however, this is what I was saying, like because we're given yearly data, and this is like the point that the book was making, you should use the yearly data in this case. But I mean, if you weren't given these guys, then you can or maybe you were just given the first one and the last one. So you can use that to compute F bar, which is the average inflation rate, the average general inflation rate, and then you can still do the conversion in that case. It's just a different, I guess, question. Okay. All right, so now let's do part C. So part C is asking us, well, it's assuming that we filled in these values here, which I mean, we haven't really. I mean, we did it, but I didn't put them in here, right? So assume that now we found, so by the way, I mean, I'm only showing the solution here for 2 rows, right? So this row and this row. Of course, this one's obvious, as we said. You could do the same thing in this for this row and this row. The difference is you're gonna have to find, of course, more annual inflation rates, and then you're gonna have to multiply them. You have to include them. So this one, this guy here, is gonna have 3 multipliers, right? Because it's 3 years. And Tiger Woods is gonna have 4, okay? So you can use that and you can fill in all of these values here. And so let's assume that we've done that. Now, the question is asking about the growth rate for the constant dollars for the equivalent prize money in 2006. So this is kind of similar to what we've done here, except now we use these values here. So there's nothing really new. And so you see here, this 122,500, right? It's here, it's this value, which we copied over here directly. this 114779 value is actually the value that we get from converting this value. So that's what's going to be written here. Okay. And so I want to find the average growth. So I take this as my F, I take this as my P, I plug in, and I find the growth over 4 years to be 2.38%. Okay. Finally, the question was asking, what about 2007? Right. So what is this value here? Assuming that the growth rate stays the same. And how do I do that? Yes, Mazen?
We multiply the prize money in 2006 by the growth factor in the actual dollars.
Exactly. So if I go back, so this is the growth factor or the growth rate for actual dollars, right? I just need to take the last value here, the 2006 value, and assume it's going to increase at that same rate. So what I do is I just grow it by that percentage. And I find that this is the expected prize money in 2007. Of course, it may not actually be this value, because remember, the value, the growth rate, G, that we computed, is an average. Sometimes some years it grows more, sometimes it grows less, it varies. But on average, I mean, we expect this amount to be the 2007 prize money in actual dollars. Okay, so hopefully now you guys understand how to go from constant dollars to actual dollars and all of this business. There's another example here, which unfortunately is not presented in the best way because it's like pictures from the book. However, like what is done here is the same. So I'll just skip over it very quickly, like for the sake of time. Yes, Khalid?
Victor, can you go back to this example?
Yeah.
On this table, the prize money in actual dollars from 2002 to 2006, does that include the inflation rate? Does that mean that Tiger Woods, when he received $1 million in 2002, it's the same as what the guy in 2006 received after including the inflation rate?
Oh, no. So remember, when I say actual dollars, I mean what I actually give you in that year. So I'm just giving you this amount. So Tiger Woods got this amount in 2002. Jeff, or whatever his name is, got this amount in 2006. So we haven't yet figured out if this is equivalent, actually. Like, that's what the point of constant dollars is. If we had the full numbers here, you'll be able to see that they have different, like, actual value, if you will. So actually, I mean, we can see it from part C, I think. Like, if I go back, or part B, no, part C, yes. So this value here is going to turn out to be 114779. And this value, we already said, is just the same because this is the base period, right? So 1225. Okay, so this is how much purchasing power Tiger Woods had back in 2002, measured in terms of 2006 dollars. And this is how much purchasing power Jeff had in 2006, measured in 2006 dollars. So you can see they're not equivalent. They're not actually equivalent. So this is constant dollars, and that's the point of constant dollars, is to see the actual value of the money in terms of what you can buy. And this is just the amount that you receive. Okay?
Yeah, it's clear now. Thank you.
Okay, you're welcome. All right. So this example is kind of similar, so that's why I'm going to go over it very quickly. I encourage you to look at it, just understand what's going on, because I mean, it's a bunch of pictures, so it's not super clear sometimes, but it's in the book anyway. So I think it's in your edition. It's not in mine. So here it's saying, let's look at college costs, like tuition prices, right? So starting from 2000 all the way to 2000 to the end of 2011, right? And so I have the costs. So this is in actual dollars. So this is how much you receive, for example, or you will receive in the bill had you gone to school in that year. This is the amount, right? So in this case, for 2003, 2004, this is what you're going to see in the bill. This says nothing about the value of the money. It says you're going to pay this much in that year. And it's asking you, so what is the question asking? It says, well, first of all, adjust the actual dollar cost to constant dollar costs with 2000, which is the first time period, as the base period, which is kind of convenient. And you're given CPI values for every year, right? And so, of course, based on what I said before, if you're given CPI values for every year, compute the annual inflation rate. So you have to go year by year. And this is why they're doing it in a table, because Excel makes it very easy. Otherwise, I mean, it's going to be a lot of calculations to do by hand. So you compute the average inflation rate for in this case, like F1, using these first two values, and then you compute F2 using these second two values, just like we did in the golf example, right? So you find the annual inflation rates, and then you can do the computations. You can do the conversion very easily. All right, so I'm just going to go over it very quickly. We see here, so here they switch things around. So the CPI is now here. So these are the CPI values. And they computed the inflation rates, right? And because we're using CPIs, these are general inflation rates, okay? They found the values. And now, of course, remember now, because I have all of these different rates, I can't just use the 1 to the F, right? Or F bar to the power N. I would have to use 1 plus F1 bar, you know, etc., right? So I have to multiply them together. And so that's what this is here. So this is, they've done the multiplication, and these are the multipliers at the end. So let's quickly maybe see what's going on here. For this value here, so this is the constant dollar value at the very end, right? Converting the actual dollar value, which is here. So this is the actual cost that was given to us, and this is the answer that they found. How did they find this? Just at a very high level, they discounted, right? Why? Because the base period is in the past, so you need to have a negative exponent. So you see here, all of the multiplying is done in the bottom, which is equivalent to having a negative exponent. And you need to take all of these inflation rates, right? So F1, F2, blah, 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 all the way to the end. You compute that, and then you find your final answer. So I'm sorry I'm going over this like fairly quickly, but because there's nothing really new, and it's not really, I mean, it takes time to go in details in this example, but it's almost exactly the same as the golf example, just with different numbers and more time periods, okay? And the only other difference is that the base period in this case is actually in year 2000. It's kind of in the past, not in the future like the golf example, right? The new thing in this example is actually here, which is, I mean, it's not new, it's just a point that they're making. They're saying, if I compute the average general inflation rate, so this is F bar, so average general is F bar, remember, over 10 years. So I use my F, I use my P, it's over 10 years, so I divide by 10 here, and the exponent, and I find that the average general inflation rate, so for the whole economy, is about 2.45%, about 2.5%. I can compute a specific inflation rate for the price of college. And that's what they do here. So if I go back here, erase the pen so we can all see, I can take this value here, and I can take this value here. So this is going to be my P, this is going to be my F, and I can compute an average inflation rate for these actual costs. Same thing as we did with the prize monies in the previous example, right? In actual dollars. And if I do that, I find this value here, 8%. So what does that mean? Well, that means that the price of public college tuition and the fees has increased much more quickly than the average inflation rate for the economy, right? So that's just the point that they're making, and they're here. I mean, I guess it's also useful to compare average general inflation rates with sometimes specific inflation rates. So you can find out like which goods and services have grown faster than the rest of the economy, and which ones have grown slower over time than the rest of the economy. Okay, so this is the only thing that's kind of new here. I mean, it's just a point that they're making. All right, so now let's turn our attention to our analysis, right? Our equivalence calculations, which if you remember is the final objective for this chapter. So now we know a bunch of things, right? We know about inflation. We know how to go from constant dollars to actual dollars, and of course what each of them is. And now we want to do analysis, right? We want to be given a cash flow, and then we want to convert things. F given P, P given F, P given A, all of that business that we've been doing, okay? And so first, let's introduce some terminology that's going to be useful, and then we're going to dive into the analysis details. And so it seems like we're not going to be able to finish this chapter today, so we'll finish it next class, inshallah. Okay, so first of all, there are two types of interest rates that we need to be aware of. And of course, by now you may be saying, how many types of interest rates are we going to cover in this class? We've seen nominal interest rates, we've seen effective interest rates. Now we see inflation-free interest rate, whatever this is, and I see a market interest rate. So what are these? Well, the good news is that market interest rate is kind of exactly what we've been using before. In fact, everything that we've seen before is a market interest rate. So I'll just write maybe here interest rates. So just to give you like a diagram so you can see what's happening and put everything together. There are two main types. And in fact, these are the two main types, right? So there's a market interest rate, which is I, and there's this inflation-free, which I'm just going to write as IF, right? Interest rate, which is I prime. So these are the two main types of interest rates, and we'll see what these mean. Okay. So, but for now, just know that we have these two classes of interest rates. So what about nominal interest rates and effective interest rates? Well, those are actually market interest rates. So those kind of fall under this category here. So the nominal and the effective are actually here. So what this means is that the inflation-free interest rate that we're seeing now, this is something completely new. And we'll see on the next slide what this really means. But this nominal and effective business that we've been doing, these are really market interest rates. Like remember, you're usually given a nominal interest rate, like APR, for example. And the only time you need to do anything, the only time you need to convert it into an effective interest rate is when the time periods don't match. So we do that to find the more accurate interest rate that is applicable to the given time period, right? So these two things are kind of equivalent or kind of the same. It's just that one is given and one is used for computations. But they both fall under the category of market interest rates, okay? So this is just sort of the general picture, so you kind of have some context and you're not scattered, like we have 4 different types of interest rates, right? So it's really market interest rates, which are the same as nominal. You can think of it that way, which is everything that we've been doing so far falls under this category, right? And then this is the new one, okay? And in fact, if you remember, if you go back to chapter 2, you look at the assumptions. So we said the cash flows are going to be in actual dollars, and the interest rate I that you're going to be using is the market interest rate. So everything that we did in chapter 2, and in fact, everything that we did in chapter 3 is in this box. Okay, and we're going to see what these mean, like what is a market interest rate and what is the inflation-free interest rate. Okay, and also we said that you can be given 2 types of cash flows, right? They can be constant dollar cash flows and they can be actual dollar cash flows. And based on the cash flow that we're given, we want to do some analysis. And so they conveniently call them either constant dollar analysis or actual dollar analysis. And in fact, in actual dollar analysis, we'll see that we have 2 different approaches for doing our equivalence calculations. All right, and so we'll go into each of these in details, but this is just showing you the outline of what we're going to cover for the remainder of this chapter. So the first thing is the inflation-free interest rate, which is the new interest rate that we haven't seen before, so this I prime. So this I prime is actually related, first of all, to constant dollars. Right, these things go together. And what this really measures is the true earning power of money, as you see written here. Right? So suppose I invest $100 today. I look at my bank account 1 year from now, and I see $110, right? I invested in a savings account, for example, and I see $110, right? Now, you may say, oh, I've earned 10%. But of course, I'm talking with actual dollars at the moment, right? So this example is like the example that we face in everyday life, actual dollars, right? So you put in $100 in your bank account, a year from now, you see you have 110 in your balance, all right? So at a first glance, you say, hey, I've gained 10%. That's great. But did you really gain 10%? And if you think about it, the answer is not necessarily, because your money also lost some value. So your net gain, if you will, is not really 10%. Because of inflation. So for example, maybe inflation was 3%, and then that means you really gained 110 minus $103. That's sort of the profit, the true earning power of that money that you've made, right? And so in that case, your I prime is going to be the 7%, okay? So it measures really how much you earned in terms of purchasing power, not just in terms of like the dollar amount, okay? And so sometimes this is also called as the real interest rate, which if you remember, constant dollars are also called as real dollars. Okay, so this already shows a connection between the two, and we'll see that connection later. Okay, and you can compute this actually from the market interest rate, which is I, and if you know the inflation rate. We're going to see how we can do that later. Okay, so there's a relationship between market interest rate, inflation rate, and inflation-free interest rates. So all of these three parameters here, 1, 2, 3, are kind of connected in a way. Right? What about the market interest rate? So sometimes, as I mentioned before, this is known as the nominal interest rate. This is your APRs that you're given. And this, of course, is really the interest that is reflected on your balance. So if you go back to my example, when I invest $100 and I see that it has grown by 10%, the market interest rate is 10%. So I, in this case, is 10%. However, the true earning power is how much additional purchasing power I've earned. That is the inflation-free interest rate, which may be something different, okay? Sometimes this is also known as the inflation-adjusted required rate of return, which is long term, but I mean, it's just there for you, for your information, okay? And actually, market interest rate is what companies and banks are gonna be using mostly in their projects, right? And even like when you get a credit card, they're gonna give you an APR, which is a nominal or a market interest rate. They're not gonna tell you how much your money actually earns, for example, in a savings account when you invest, right? They're gonna just give you the market interest rate, and you can actually figure out based on the inflation rate how much you're really earning in terms of purchasing power, which is this inflation-free interest rate business. All right, so now let's turn to doing analysis. So you see here, I've already hinted at this, constant dollar analysis, which is using these primes, the constant dollars, is related to inflation-free interest rate I prime. And actually, I'm just gonna skip ahead. Actual dollar analysis, which is exactly what we've been doing in chapters 3 and 4, is related to the market interest rate, I, which makes sense because, I mean, I told you what we did in chapters 2 and 3, we're using actual dollars. This is the first time we talk about something other than actual dollars. And we always used I as given, right? And so this consists, or this is consistent with what we've covered before. And so now let's go back to constant dollars. So to do constant dollar analysis, usually we do it when all the cash flow elements, the cash flow diagram, for example, that I give you, everything is in constant dollars. So if I do that, then maybe I can do something called constant dollar analysis. And what I can actually do is I can find the present value of the sequence of payments that is given in constant dollars. So you can see here, I compute the equivalent present worth of constant dollars in year N, in any year, right? Year 0 could be another year. However, the key thing is here, the interest rate that I use is I prime. I do not use I, right? So in constant dollar analysis, if I'm given a cash flow that consists of constant dollars and I need to find the present value for it, I'm gonna use I prime as my interest rate. So that's, okay, like that's key here. What about actual dollar analysis? Well, that's what we've been doing before. All the cash flow elements are estimated in actual dollars, right? So I give you a cash flow where everything is in actual dollars. So I tell you everything here is actual. I can still find the present value, which is in fact exactly what we've been doing before, right? So in any given year, I can find the present value. And here, well, you see here, I mean, it's related to market interest rate. So I can use I, which is what we've done before. In fact, if you remember, with actual dollar analysis, there are two approaches. One of them, which I think is this one, is exactly what we've been doing before. I mean, it has a name, which is adjusted discount method. We'll see why that is. But for now, it's exactly what we've been doing before, right? I give you a cash flow diagram with actual dollar amounts, and then you convert it to present value, and you use I, the market interest rate, to do that conversion. In some cases, however, you will actually be only given I prime. Remember, I prime goes with constant dollars, right? So here I need to do something different. I can't just move these guys back in time using I prime. I would have to do it in 2 steps. For example, at least like in one of the approaches, I do it in 2 steps, right? And so if you're given I prime, well, one step, well, there are 2 ways here you can do it, right? So one way is to, from I prime, if you remember, if you have I prime, sorry, if you have I prime, and if you have F bar, I can compute I. I told you all of these 3 things are related. And so then if I compute, I can do the same thing I've been doing before, right? So that's one approach. The other approach is to say, oh, I'm given things in actual dollars, but this is related to constant dollars. So what I'll do is I'll convert each of these actual dollar payments, each of these arrows, to constant dollars. Okay, so I'll change them all to constant dollars, and then my cash flow is going to be in constant dollars. And then I'm going to move them back using I prime, which is exactly what we've done in the constant dollar part. Okay, and we'll see some examples on this, but hopefully, I mean, you see the general picture here. Okay, and so just to wrap this part up, and then we'll continue next class. With constant dollar analysis, the inflation rate that you use, the interest rate that you use is the inflation-free interest rate, which is I prime. I prime. The cash flows are going to be in constant dollars, I mean, which matches the name. And it's called constant dollar analysis, right? That's the analysis method. With actual dollars, you're going to be given a market interest rate, or sometimes you're going to be given I prime, but you need to convert it. Like you can't use it directly, okay? But the one that goes with actual dollar analysis is the market interest rate I. And then the cash flows are going to be in actual dollars, of course. And we're going to do actual dollar analysis using actually two approaches in the next class. So that's what we're going to see in the next class, and we're going to cover some examples, and then that concludes this chapter. Okay, so I'll answer your question, Sultan, for now, because I'm already over time. Look out for the homework, which is going to be posted tomorrow, inshallah, and I will see you guys next week. I hope you have a good weekend. So I'll stop recording, and then I'll take your questions, Sultan, sorry.